Now we're going to study the magnetic field of a toroid. Magnetic field of a toroid. So we need to draw a toroid. So you have, it's like a solenoid that you bend over. So you have like a solenoid like this, and then you bend it. So you get something like this. So this is solenoid. This is toroid. So what do? Let me make a big one here. So here is a toroid, like that. And you want to find the magnetic field inside the toroid, there. I want to find the magnetic field there. So we have a current. Let's see, the current is going. Here is the current I. So we have a current here. Let's see, it comes in. So let's see, the current is going in here, there, going into the page. Okay, like that. So this is the current. And this coming out is going in here and coming out here. See the current going in, coming out here. See, like that. Now we need to find the magnetic field there, in this region that I'm showing you with the pen here. We need to find the B field at that location. We need to find that B field. So what do? We draw an ampere loop. So take an ampere loop like this. Here is an ampere loop. And then I put here B dot dl is equal to mu0 times I enclosed. Let's go look at the right side. I enclosed, the current that enclosed in the loop. We have 1, 2, 3. Let's start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 current inside here. So instead of putting 11 current, we just put Ni, and N can be any number. The number N is the number of loops, and you can choose any number of loops you want. The more wire you have, the more loops. So the right side of the equation is simple. We just put here B dot dl is equal to mu0 Ni. And here is the right side of the equation. Now we need to tackle the left side. For the left side, we go here. I put B dot dl. Now, since we have the same current in the loop, and we try to find, let's see, the B field there. Now, these currents are the same distance from where I want to find the B field. See? Same distance. So the distance is the same. The current is the same. So the B field is constant throughout that loop there. So the B field is constant. Okay? Now, so this B here is a B field. We can just, it's constant, we can get it out. Let me put here, this is equal to integral of B dl cosine theta. Okay? BL, the cosine theta. You see, the B field is perpendicular to the L, dl. dl is a section of the loop. Let's take, for example, dl is a section of the loop. Let's take some dl, for example, here. This is dl. I remember, I have to be careful here. You see here? This is the ampere loop. So I put here dl. I'm going along BDL along the ampere loop. So I take this section here, put it DL. Let's see, this section here, DL. You can choose this section here, DL. You can choose which DL you want. Now, the B field, like in the solenoid, is going to be actually going along that DL, along the loop, the ampere loop. So they're going actually like parallel to each other. So DL will be going like that, this DL, and you also have that B, the B field is also going like that, parallel. If you come to this section, DL is going like that, the B field is going like that. In this section here, DL going down, the B field is going down like that. So the B field is following DL. DL, B field. DL, B field. See? So the B field is parallel to DL. So this theta is 0. So this is just 1. And since the B field is constant, it can come out of the integral. So I have B integral of DL is equal to this. I put here mu 0 Ni. Now I have to integrate this DL. These DLs are small sections of this circumference. Small sections. And then I keep adding them up as I integrate. So when I finish, go around one cycle, I'm going to have the circumference. So this DL, when you integrate it, you're just going to get the length of this circumference. So I just put here B, L, mu 0, Ni. Now, this L is the circumference, which is 2 pi r. So I just put B, 2 pi r is equal to mu 0 Ni. So the B field is equal to mu 0 Ni over 2 pi r. Here is the B field of a toroid. Now somebody will come and say, hey, you did too much work here. Too much work. Why don't you just do this? We have a solenoid. Okay, here is the solenoid. And he or she is going to say, we found that the B field is equal to mu 0 Ni over L. This is for the solenoid. Now, when we change the solenoid into a toroid, go like this. This L here, that we have here, it becomes 2 pi r. And this is the radius. So 2 pi r is L. So you don't have to do all these calculations. You can just put here mu 0 Ni over 2 pi r. And then you get the same answer as on the left here. Is mu 0 Ni over 2 pi r. So just get the B field of the solenoid and then take the solenoid, bend it into a toroid, and then instead of L, use 2 pi r because the circumference is just 2 pi r. And you get the same answer here and there. Okay?